will come tomorrow before 9 a.m. You need to do that around 9 a.m.
So can you come?
Yeah, I will come to the desk.
Okay.
So will you need from here?
Well, I'll wait for you. So don't worry about that. But,
Thank you.
Oh, it was like 2016.
Wait.
Oh, like the style? Yeah.
But the current style is different. I have that in good stuff. Like it's like a chain like this. So
Yeah.
It's like a Yoga 900. Except that thing broke.
All right, I think we should get going. How's everybody doing? Like, how many weeks in are we? 5 weeks? 4 weeks? 4 weeks? 4 weeks in? Seems like 5. Yeah. Seems like 45. We're in September. Rolling. How's the homework going? Raise your hand if you started it. Ooh, good. Raise your hand if you haven't started it and are like, no problem. Raise your hand if you haven't started it and you're like, oh my gosh, I haven't started it yet. Nobody. Good. All right. No one wants to meet. For those of you who have started it, anybody finished it? Kind of? Some? You finished it?
I almost finished, but just the verification accuracy is not high.
Ah, yeah. Machine learning is hard. Yeah, that's good though. Good job getting that far. Yeah, so these homeworks and the next set of homeworks will start. I haven't put them up yet, but I'll put them up hopefully tonight, probably more like tomorrow. They're very much the same as this, the style of this one. A lot of people say, no, don't put them up already. They're very much in the style of this one, where it's, again, like you're having to think through all of the calculations for different types of layers. In this case, we're going to start doing convolutional networks today. So you're basically going to be doing the same kinds of things that you've been doing, but doing for convolutions, for batch normalization, for dropout, for the things that are more like what we think of as deep learning these days. But you're doing it, of course, all in NumPy, not forcing you to write it in C++ or compile that to CUDA or something like that. So you can debug it a lot easier and go over those other languages. Any questions before we get rolling here on the lecture today? All right. Well, today we start on convolutions. So we thought we'd never get here, but here we are. Convolutions. So we're going to start into a couple weeks of learning about convolutional networks. And today, the idea is to set up like the basics of convolutions, like what does a convolutional layer look like, and yeah, just all like a lot of the basics around that. And then the next 3 lectures after that, we're basically going to go through like just different architecture. We're going to kind of do it in chronological order, starting with like what's thought of as like the kind of the earliest successful convolutional network, and then kind of working our way through the networks that started winning the Imagenet classification challenges. So this would be things like AlexNet, and we'll work our way through a couple of those like iterations on that. We'll get to ResNets. We'll get to iterations on ResNets and those kinds of things. So like we'll get quickly these next couple of weeks into networks that are like bread and butter networks for doing convolutional work, like right now. So it'll be pretty fast paced, but hopefully this is the kind of thing you sign up for when you sign up for a class like this. You wanted to get in and understand these kinds of things, like really what's state of the art in convolutional networks. All right, so
You adjust the lights.
oh yes, I forgot all about it. Let's see. Thanks. Actually, I looked at the two and I was like, I can't see it. Okay, so yeah, so a little bit of history here. So these feed-forward networks that we started learning about last time, like one of the first implementations of them is this machine you're seeing over here, known as the perceptron. And these are just feed-forward networks. There's a fancy name, perceptron, but it's just a feed-forward network with a single hidden layer. And then you might hear multi-layer perceptrons, and that's multiple hidden layers in a feed-forward network. So just kind of the same thing that we've been seeing before. Although you had this in this very early implementation, you had this activation right here, a step function activation, which we didn't actually look at, and not really a great one if you think about it, because of the lack of gradients. In fact, the update rule used in these early work looked more like this rather than the actual what am I trying to say? Like the gradient step. So we're not going to spend any time kind of getting into this, but just know that way back in the 50s, people started kind of working with neural network-like things, and they were implementing them on these awesome old pieces of hardware, Mark I. Rosenblatt published a paper in 1957 on this, and this was able to recognize letters of the alphabet. Really long paper, so there you go. Pretty cool. If you see here, it says it's using these cadmium sulfide photocells. So you basically hold up this big picture of this written thing, in front of the photocells, and then that's how that was encoded. Okay, so great. There was a little bit of kind of building up from those ideas. You had this really kind of funky architecture called the neocognitron that wasn't convolutional necessarily, but it had some of the architectural pieces that we use even today. Think ideas called pooling, and we'll get into what pooling is today. But ways of taking the spatial dimensions and kind of reducing those in advantageous ways. So this is in 1980, and then in 1986 we get this paper, Revelhard et al., where backpropagation was used to actually train these things. So there were all these kind of different update rules up until someone was like, hey, if we have a differentiable objective function or loss function, then we can update the weights using backpropagation, using the chain rule. And so now we get a very crucial part of what we do nowadays in training neural networks, backpropagation. And then we get, in 1998, we get this, what's called LayNet, or I guess technically LayNet 5. And this has got some really big names in machine learning, in deep learning. So Jan LeCun, anybody know who Jan LeCun is? Probably, if you follow any deep learning, you know who he is. Leo Buteau, Yoshua Bengio, and I'm actually not sure who Hafner is. He didn't make the list of all the people who are famous. But LeCun and Bengio actually just won the Turing Award this year for their for all this work over the many decades that they've been doing it. Along with Jeff Hinton at the University of Toronto. And this is probably the first modern-looking convolutional network. I don't know if it's the first, but it was the first published that had some sort of success in recognizing handwritten digits. And it's convolutional, so it's actually got, it takes its input, it will do, and we'll get into what the convolutional layers are like, but it performs this convolution with these smaller spatial filters, and that maps our image into a set of feature maps. Then we do that process again to a set of another set of feature maps. Do it again, and then these get transformed into a fully connected layer, and then we have some fully connected layers, and then finally the output, the loss function, trained with backpropagation, and we learn to read handwritten digits. So LayNet is a very basic convolutional network, and like, again, like this is like the first, and you can see why it's called LayNet. These always get, like the first author gets their name somehow put in there. So Cocoon, LayNet, yeah.
What exactly does fully connected mean? I've seen that also in the homework.
Okay, so what that means is it's like everything we've been doing so far. There's this input layer of dimension M, this output layer of dimension N, and there's like a full weight matrix between them, N by N. What makes it fully connected is that all of those weights can be non-zero. Like they're like it's possible for each input here to be connected to each output here. So it's fully connected. And you have a couple of layers like that. That process the output from the series of convolutional layers to the final output. Then into a loss function. Okay. Yeah, so that did well, but this was 1996, so there still wasn't like great compute. Like you really couldn't have a very deep network here, so you couldn't learn a whole lot more than just very, very simple representations of images like these handwritten digits. And I I wasn't paying attention during these years, but I guess things just didn't progress very much. And then Jeff Hinton, which is the other name I mentioned, who won the Turing Award this year, they start doing these things called restricted Boltzmann machines, which we're not going to learn about, but it was this way of like doing something called autoencoding, which we'll learn about. But it was a way of initializing weights for much deeper networks than had been trained before. And so you got this initialization, and then once these weights were initialized, then you could actually like learn in these deep networks. And all of a sudden, like you could do things like learn to compress this image into a much smaller dimensional space, and then recreate it, decode it, so to speak. So like the kinds of things it was learning were the capacity of this network was now much greater because it was able to be deeper, which is really cool. But like the whole thing about restricted Boltzmann machines was it was difficult to train, difficult to tune. Seemed to only work for a couple of examples that were used, and lots of research going on there. And finally, like the first major success, I guess, recognized success for convolutional networks was in winning the Imagenet classification challenge in 2012. Again, Jeff Hinton on this paper, same from 2006. Using a different style convolutional network, a lot more like LayNet. But all of a sudden now these are like this wins by a lot, and then every year after this, there's updates to the convolutional networks that win this contest until like in 2015 or 16, I can't remember which year it is. We'll have some slides on that next time. All of a sudden, now the networks are doing better than human ability to human error levels in doing the classification, and in some sense, it's like this paper, this result, that sort of sparks the whole revolution in deep learning. Like it now is becoming a thing. Like, whoa, we can solve really complicated problems, right? Instead of just recognizing an alphabet, a handwritten alphabet, we can now recognize that which of 1,000 objects is in each image over millions or over a million images. So major results. So that's actually called, not surprisingly, AlexNet, because of course Alex threw software there, so AlexNet, and that like again, this starts the whole convolutional network revolution, really the deep learning revolution. Yep.
Can you explain that picture at the top right?
Yeah. So this is a representation for these earlier results. Again, one of them having Jeff Hinton's name up there. So this acoustic model. So taking the spectrogram of the time series for the sound signal essentially, and I can't actually remember what the task is here because they're using deep belief networks. I can't remember, but what you're seeing here is just like this is output. There's layers of this network, and there was a pre-training step done here using a hidden Markov model, which is like a time series model to initialize the weights. So it's a latent variable time series model. So the latent variables were the weights in the layers. So like those were pre-initialized, and they were able to get. I would say right now I'm forgetting what the task was there. If it was just to like be able to represent this in the images before where you auto-encode the sound signal, or there was like recognizing somebody's voice or something. I can't actually remember. But again, it's just like it was kind of in the spirit of the previous result where you use these other existing latent variable models to pre-train the weights. But that wasn't done here. There was just sort of like a statistical approach to initializing the weights, and then just training from scratch. Yeah.
It's both based on the human perception, you based on the average of the human perception.
Yeah, right. So like I don't know how many. There's a level set for the Imagenet classification. So a certain number of people went through and classified. It'd be surprising if it was all the images, but in the test set, there were quite a few, but tens of thousands. But yeah, so like a number of people did it. The average that they. And Imagenet's funny, right? Because it has like has things like automobile and airplane and things like that. But then it has like subspecies of dogs. So like you might think like because humans are making something like 3% to 4% error, I guess the error rate. But it's usually amongst all these like very specific dog breeds that most people don't know how to recognize. But the convolutional methods learn to recognize them essentially. Okay. And I explained one piece. So, what we're looking at here. So, what we're seeing here is this is the architecture of AlexNet. It's really weird. It's split into two pieces, and I'll talk about why it's split into two pieces. And also, this is also very weird that like the top of this is missing. But this is how it was published. It's at the top of the page, in like on the 5th page in this paper, and the print, the typesetter set it this way, so it's missing the top. So whenever AlexNet this is like a historical accident. Whenever AlexNet is displayed, you're always missing the top of it. So that's kind of a funny thing. And then what you're seeing here, these are the filters, the convolutional filters from the first stage here of the network. And what this is showing is that what it's learned are filters that, so like the colors and the intensities that you're seeing is some representation of how large or small the weights are in that filter. And the reason that there are colors is that because these are the filters from, and I know we haven't done this yet, so we're going to get there in just a second. But because these are the filters for the first layer, and Imagenet is comprised of RGB images, what you have is you have a filter with, again, 3 layers, RGB, and so you can actually visualize these as colors. And what you see here is just a lot of like edge and frequency detection in different orientations, right? So some of these are really clear to see, right? This is like a very clear horizontal edge detector, right? With like the weights are very high here, and weights are very low here. So it's like if there's an edge here, like this represents like there's a building, and it's like lighter here and darker here. When you do this convolution here, that'll create a large number, and you'll be able to see that there's an edge there. And that's like there's black and white there, so that's kind of a more like general color pattern. But you also see like a lot of repetitions of the same kinds of edges, but for different color patterns. So the point is like what's this learned in its first layer? This is learned edge detection in various orientations and colors, which is, and at different frequencies too. Like you can see some of these things are not necessarily edge detectors, these are more like texture detectors at different spatial frequencies. Yeah, wait, so the first layer of convolution, so these are just, again, like they're just plots of these RGB convolutional filters from the first layer. So like from the image to producing the first feature maps.
Are there any possible way to draw the second layer or third layer because they are not the third dimension?
Yeah, that's right. Like you can't just like do this because those filters are, like in this case, they're going to be 48. They're going to be some spatial dimension like 5 by 5. I think is what it is in AlexNet. But the depth will be 48 channels rather than 3 channels. And so, like, how do you visualize them? I mean, of course, you can imagine ways to visualize them, but they don't like represent like a natural. This is like one of those things about convolutional networks is, like you always see pictures like that for the first layer because you can visualize them so easily. But like really, what's happening as you move down? And there's some techniques for visualizing that, and people create ever more techniques for that, but. There's really no like a priori like obvious way to visualize what's going on. Okay. This is just calling this out one more time. AlexNet. It's always missing the top. This is how it is. Okay. So, now convolutional networks, ConvNets for short, are just all over the place, doing all kinds of things. And everything from like basic classification to using representations or embeddings of images to find similar images to some query image. That's what we're seeing here. So like very, very effective ways of looking at what's nearby. And if like you've been working on this with the linear classifiers, we talked about how if you look at these images that are close in some sense, they're embeddings in the networks close to each other. If you just do the pixel space, it doesn't really make any sense. But if you have a network that's learned to like classify these things, and you look at the representation, the embeddings I'm talking about here are like take the vector right before you classify, it's right before the softmax layer. Think of that as just like some compression of the image down to some n-dimensional vector, and then you start looking at some compute similarities between vectors. What you'll often find is if I take the representation for this elephant and then I look at all the other images that are in some sense close to that in that particular space, I get lots of elephants. And it's not just elephants that are like oriented or positioned like in exactly the same way. They all have just elephant characteristics. So like this embedding, this representation that this thing has learned is like insensitive to things like where exactly the elephant is in the image, how exactly it's oriented, which way it's facing, things like that. It's learned like more abstract characteristics of an elephant and able to pick it out, and so on for the other objects. So like a super useful technique, and like some version of this is working in something like Google Images where where it will retrieve. But there used to be, is it still available where you can give it a query image and it will find all the other images like it? There used to actually be something like that.
Yeah.
Is there still there? Yeah, I don't think I've used it for a long time. Anyways, things like that use like these kinds of techniques, but far more sophisticated than I'm sure that we'll cover in this class. Like we've already kind of gone through some of these. You can do things like detection of the individual objects within the images, segmentation of all the objects. So this is something like, can I draw a box? So basically, can I put 4 points on the image that surround an object and then classify what's in that bounding box, it's called. This is very different, where every single pixel gets labeled, and not only that, they get brought together in kind of coherent objects, right? So like all of these kind of reddish pixels represent individual people, and the grayish ones are the road, and there's some for cars. You can see this is actually getting some of these wrong. It's thinking shadows are cars, the trees, plants, buildings, so forth. So and these are really powerful things. We'll learn about how these are done. We've already talked about the self-driving cars use similar technologies. There's lots of things. Pose estimations. You're kind of seeing this. Like where are this person's arms and the joints, shoulders, chest, things like that, and I don't know, so many other things. Like there are networks that learn to play like old Atari games and video games, and they use convolutional networks to understand what's going on in the frame of the video game that they're in right now, and then be able to decide on an action to take from that particular frame. So many other cool things. This is like classifying tumor whether they're malignant or benign. This is classifying different types of galaxies. I don't know how that's cool or not, but recognizing different signs, that's important for self-driving. There was a Kaggle challenge a couple of years ago around recognizing like what species of whales were in the water, where they were in the water. This is like recognizing where roads are in images. This is helpful for satellite imagery and like mapping out what's going on. We saw stuff like this. Now this gets even more like combining different kinds of networks, like convolutional networks with recurrent networks that produce sequential data. So this is like, give me the image and I tell you what's in the image, and I give you a natural language sentence. So everything from like exactly right, a white teddy bear sitting in the grass, to a woman holding a cat in her hand. It's like not quite right, but you can see why I got it wrong. She has a very cat-like robe on or something. So yeah, these are really amazing, and you can see, like, I haven't been putting these out, but you can see the years on these papers and where some of the stuff was published. And remember, in 2012, AlexNet wins the Imagenet classification challenge, and then already in 3 years later, 2015, we have the ability to write, for the most part, good captions for what's in the images. So like a lot of progress, really, really fast. Yeah, there's other cool things that we'll learn about, like style transfer, deep dreams, these are ways of understanding what's going on, like what's a network doing. I mean, they're like more like just kind of fun ways of thinking about it. Like, what are the kinds of objects that get reinforced by a particular network? This thing of style transfer is really fun. You can take a photo and then take the style, and take another image and transfer the style while preserving the content. We'll learn how to do that as well. In fact, you even have homework stuff. Okay, so this is what we're doing. Okay, so convolutional networks. So the first way you might think of for dealing with images is to not think about convolutions at all, but just kind of go right into what we've been doing, which is fully connected networks, right? So I could have image sets that are like 32 by 32 by 3. This is like CFAR 10. And yeah, when I say 32 by 32 by 3, it's always width, height, so 32 by 32, and then 3 channels. So usually there are 3 because we have 3 color channels from which we make all the channels or all the colors in the image. So one way to just kind of deal with it is say, like, let's just stretch that out in some predetermined order to a 32 times 32 times 30 or times 3, which is 3072 length vector, and then do what we've been doing, like just do fully connected network. So like in this case, have a single layer, or hidden layer. You might have more, and you could do this. And remember, what happens here is for basically each row in our weight matrix, that's producing for us. After we apply that activation, that's producing for us a single number. So that number again is coming from like a row of the matrix. That's a dot product with the input vector x, and that's giving us a single number that goes into the output of this layer, and we do that for all the rows. Convolutional layers do something quite different. So one of the issues with what we just did right there before was that we sort of, not entirely, but we sort of like ignore that there's spatial structure in images by just sort of like stretching it all out and then applying some fully connected weight matrix. So first of all, like those weight matrices are huge, right? They're 3072 by 10. And they aren't really like structured to think about the fact that in images, there's really like spatial coherence. Like you take any sort of part of the image, there's like some statistical coherence of the pixels that are in any kind of subregion of the image. And we want to be able to take advantage of that so that we can create networks that don't have as many parameters, but do just as well, or we hope way better, than just treating these in a naive way. So, like the very successful approach here is to use convolutions in convolution layers. So the way this works is instead of there being some fully connected matrix that sort of spans all the entries of this, what we do is we take a smaller, in this case 5 by 5 by 3, it could be whatever size, but notice that that's much smaller than the size of like our input image here, 32 by 32 by 3. And what we're going to do is we're going to take this, and we're basically like, there's, 75 parameters here. We're going to do a dot product of that with like different 5 by 5 by 3 regions within this image. And that's going to produce for us a different number, and we're going to kind of just slide this weight matrix, or this weight tensor, all over the image, and we're going to talk about different ways you can do that, and produce a number for each time we like move it, and that's going to give us output for the next layer. We'll apply an activation of that, and that'll be the final output for that layer, and then that'll feed into the next. But the idea here is that we're going to be using these much smaller filters. And let's do it. Click here to the slide. So this is like almost always the case where your filters, while they're going to be like the spatial dimensions are going to be smaller than the spatial dimensions of the input. The number of channels, we often refer to this third dimension in the tensor as channels. That's always going to be the same as whatever the input tensor size is. So if this is our original input from the image, there's 3 color channels. There's going to be three layers here in this tensor. Layers is a bad word to use there. Just 3 different slices through this tensor. So there's like 3 5 by 5 matrices kind of stacked up together, and that's just always the case. It's just sort of a convenience thing for how convolutional layers are defined. And again, like I said, the way this works is I'm going to lay this down someplace in the image. There's going to be, wherever I lay it down, there's going to be like for each entry in this filter, there's going to be a corresponding entry in my input image here, And I'm just going to do I'm just going to do a dot product. So like wherever entries match up, I'm just going to multiply those together. I take all of those products, add them all up, and I'm going to get a number. I'm going to add to that a bias, which gives me another, just one more number. So like in this case, where I have 5 by 5 by 3, there's 75 like weights in this filter. The bias gives me one more parameter, so I have actually 76 parameters in this that produce this one number in the output. In much the same way that like when I applied my row from the weight matrix in the fully connected layer, I got a single output in the output layer. And if I, like in this case, if I just like start at the top corner here, I take this one filter, I start at the top corner, and I just sort of like slide it all around, just moving kind of one entry or one pixel at a time, like to the right and down. Then what I end up with is a 28 by 28 by 1 activation map or feature map of entries, right? So like in this, and I have some other slides that kind of go through more carefully, but like in this very first top corner here, when I do that kind of convolutional dot product, that's going to give me like the one entry that's right here. And I slide it to the right, it's going to give me the one entry right here. If I start from here and I slide it down, it's going to give me the one entry that's down there. And this is how I like fill out, again, something else of like a different, in this case, a different spatial extent. Like this is like how I get to the next layer. And then each filter is going to give me a different channel in the output. So I do this again with a different filter. So I had the blue filter before, now I do it with the green filter, and I get something of exactly the same size, but it's a different filter, so it's different numbers. And now I have two activation maps, so the output so far is 28 by 28 by 2, using both filters, and then I can do that for however many filters I want. I just get a new, for every filter here, I get another activation map. And that's the output of this layer, and that becomes the input into the next layer. So again, it'll be another tensor of some spatial extent, and then some certain number of channels. But where this, like the initial input was decided by like how big our images are, the output is determined by the size of my filters and how I decide to kind of like move them over my input, and just how many of those filters I have. Is that making sense? Yeah, question?
I'm not clear on the operation you're using, or when you're taking the 5 by 5 by 3 filter and then applying that to a 5 by 5 by 3 section of the original image.
Right.
When you say dot product, do you mean like you're taking every element?
Yeah. So like entry-wise, I'm just doing all the products, because they're laying over each other. So entry-wise, I'm doing all the products. Then I take all those products and sum them. So that's like a dot product, right? I'm getting a scalar out of that. And then I add to that a bias, which gives me one more parameter.
So it's not like matrix multiplication?
No, it's not matrix multiplication.
Oh, okay.
Yep, that's a good, it's not tensor multiplication. It's like Hadamard product followed by this like sum. So it's like entry-wise products, and then you sum them all up. So it's like a dot product. If it is a dot product if I like, if I take the two 5 by 5 by 3s, like the piece of the end of the input, and then my filter, and then I like, turn those into vectors, and then I just do a dot product. That's like the same output in the beginning. You wouldn't do that like in the computation because you don't need to do like the stretching out. It would just be like an unnecessary operation. But that's just to kind of get you to think about it that way. Yeah.
I'm gonna miss it, but how do we get an output of 28 by 28 by 1?
Yeah, well, we're gonna do more of like what determines the spatial extent here. But in this case, what it is that we're taking this 5 by 5, and we're just starting like in the first 5 by 5 corner up here, and then we're just sliding it one pixel at a time along the top. And if you think about it, what's happening is, so like 5 by 5 like how many times can I slide it over? So if I have 32 pixels in width, how many times can I slide a 5 by 5 over 1 pixel at a time? It turns out to be 28 times. Because I have, in some sense, it's like I have like the 28 by 28 like inner tensor here, and the 5 by 5, like the center of this 5 by 5 sits at that corner of the 28 by 28 inner, and so I just kind of move along. There's ways of changing that up through padding, through striding, and we're going to get to that here really quick. Other questions? Yeah.
On this signal processing, we have correlation and convolution, but this operation is more than correlation, like convolution. The elements are not new.
Yeah, I'm not sure like how to answer that. The reason why it's convolution is this sliding idea, right? So like like a true convolution, from like a continuous signal, I take some sort of filter of some size and like do convolution. That like you can think of that as in that integral. You can think of it as sliding the filter over the signal, and getting, so for every time you move your filter, you get like a different, you get a different integral, with the signal, the fixed signal, and that operation is known as convolution. So it's very similar to that in this whole idea of like a fixed filter that's sliding over your input, your signal. Like comparing it to correlation, I'm not exactly sure.
Is this green circle the filter, or is this?
No, the green circle is the output. Is the single one-dimensional scalar output from like taking this 5 by 5 by 3 and doing the convolution in this part of the image. That's just a single number. And when I range over the whole thing, I get 28 by 28 different circles that end up being a slice in this output tensor. Yes.
In signal processing, when you do convolution, you have to reverse the field.
Right. And you could technically do that if you wanted to like reverse your weights, but that is totally unnecessary, right? Yeah. You do that in signal processing to like get certain properties of the convolution, like when you apply the Fourier transform, for that to turn into the product of the two. Right? You could do that here, but it would be totally unnecessary because you're not going to do Fourier transforms with this.
So are all the values and filters trained through gradient?
Yep, exactly. Like this is all going to be trained through backpropagation, exactly the same way that we've been doing before. It's just going to be a little more complicated how we go from input to output. A couple more questions we got to cruise.
So is this kind of tensor decomposition?
Nope, not tensor decomposition.
How can we determine the size of the dimension of
Oh, how do you determine it? It's a hyperparameter. You get to decide. Yep. Everything's a hyperparameter. Yeah. There's, as we go through like the different architectures that have had success, you'll see like how different choices are made, or like what different choices were made. Maybe not how they were made, just what choices were made. And you'll see that like most convolutions, like most kind of like modern networks will have usually like a large convolution at the beginning to like capture a lot more spatial extent, but then immediately this goes to like 3 by 3, which is like the smallest filter you can have that would capture some sort of spatial correlation. That's simply for efficiency reasons, and you just have a whole bunch of layers of that. But hyperparameter, you get to tune it. Yeah, right. So these, for each filter in a layer, that's going to produce a single slice in the output. We call these activation maps. If there are 6 filters, you get 6 channels or 6 different slices in the output. And then that gives us our new quote unquote image, but it's the output tensor that becomes the input to the next layer. And it won't be an image anymore because it just has nothing to do with like RGB. But you will have a tensor, and you'll be able to do you'll be able to do another convolutional layer because it's of the same kind of tensor size. Okay. Yeah, and the way this works, like what we'll be doing here when we're doing convolutions is we will be doing those convolutions, and then we'll follow those up with an activation. And here I put ReLU because, again, remember you should always start with ReLU. It's usually going to be the most successful, and you can play with that as a hyperparameter as well. But you just kind of keep doing this, right? So like, if this is if your images are of this size, and you choose for there to be 6 filters of 5 by 5, and you just kind of do this naive convolution, then your output is going to be 28 by 28 by 6. And I follow it up with 5 by 5 by 6 filters, and I say like have 10 of those. Then I'm going to reduce again my spatial dimensions by 4 in each direction. I have 10 10 filters now, and I can just keep doing that. And this is giving the layers in a convolutional network. And that's the basics.
So is the number of the future
Hyperparameter. These are all hyperparameters that are part of your choice of neural network architecture. So like every architecture you choose is like a whole bunch of hyperparameters. Like it's like a whole family of hyperparameters. And the success of like convolutional networks is people just playing around with these things, like in a setting like the Imagenet classification task, and just finding things that work better. And usually there's like a hypothesis of like, if I do this, if I do this kind of thing, it will be better because it's not like if I have 10 filters instead of 6, it's going to be better. It's more like, if I do like a major kind of convolutional change, then usually like these choices of like number of filters, or like sizes of the spatial sizes of the filters is more just like, there's more like Occam's razor type principles applied. Like let's just do the simplest things possible, and like let's go for networks that could be like way deeper, because like depth seems to help. So like if 12 layers was great, let's get to 24 layers, and then like let's get to 50, let's get to 150, things like that. Let's get to 1,000 layers. Like there's just different ways of kind of thinking through this. So people don't really sit there and tune the architectural parameters necessarily. What they do will like you'll choose an architecture and then just tune things like the learning rate and like some other things like regularization parameters like dropout rate, which we'll get to in a second. Yeah.
Is that true? Is like 1,000 layers always going to be better than 100 layers? Or
no, again, like it's problem dependent, it's data set dependent, task dependent for sure. Again, like this is very empirical. More depth usually is helpful, but it certainly has diminishing returns, and you can get to a point where there's so much depth that like it's like not learning anything. It could become really like the dynamic could be unstable, or you could find good parameters for that, but find that like most everything's like identity map after you pass through so many layers, things like that. Yeah.
So the filter that we're using here, is it acting as a neural network, or is it just a matrix or something?
It's creating a layer for your neural network, right? So the filter is this like whole series of operations as you pass it along. I mean, you can actually, it's in very much the same way that we're doing a simple matrix multiplication to go from like in the fully connected layers from like a vector of size m to a vector of size n. This is just going from a tensor of size m by n to another tensor of size k by l, right? Like that's all connected by weights. Like there's weights in there, and that's what's giving you the neural network.
I mean, what is activated by RE here? Like,
What's activated?
yeah. So what are the nodes here?
What's activated by ReLU?
Yeah.
The output. So like these pictures right here, like you're getting outputs like this, and you just apply ReLU entry-wise to everything in the tensor. Okay, let's keep going. We got a lot more to cover. Okay, so so like I showed you before, this is using another successful architecture called BGG, and this is a visualization of actually different convolutions along the way. These ones that are deeper in the network, the way that they are showing these is like, I believe these are like PC, like we're PCAing this down at the higher dimensional channels down into 3 dimensions. We're just showing like the 3 top principal components and just giving you some notion of like what's going on there. It's not like a great way to understand this because there's a lot of variation in the rest of the tensor, but a way of visualizing kind of what's going on.
Yeah, it seems that the filter size keeps to increase as the layer go deeper. So is there a reason behind that?
It doesn't increase. It actually, it usually decreases.
Like the size of filter, yeah. But
yeah, so
filter somewhere the square is very small, but in the third picture, the filter is larger.
Yeah, so like, oh, I see what you're saying.
Yeah.
I see what you're saying. No, that is, let's see. Yeah, that's not the case here. They actually they usually get smaller because it becomes more. It's very expensive to compute like high or like large filters. And let's see, like why are they getting larger there? Yeah, I see what you're asking that. I don't remember why that is. I'm forgetting why that is. It's the representation being used, but I can't remember why it's larger. I'll look that up and
So the later filters will sense more large area.
yeah, like that was my sense too. Like what these might be corresponding to, which would be weird, is the what's known as the receptive field in like the original image. But that would be kind of weird because I don't know. I have to look that up. I don't think it's a receptive field. We'll talk about receptive field in a second. Oh, we can talk about it right here. Yeah, but that's not what these are. So I'm not sure. There's this notion of receptive field in neuroscience, which is like look at any point in space. There's a certain part of like your primary visual cortex that's processing that, and let's see, do I have it here? You have the same kind of notion for like in any layer, any feature map. You can take the activation, you kind of work your way back through the layers to see what were all of the like pixels in the original image that contributed to that activation. Because of the way activation or the way that convolution works, because it's like spatially restricted, not all the pixels are going to contribute to all the activations. It might be that you've chosen your filter sizes and the number of layers such that like eventually it covers the whole space, but that's usually not the case. Here's a slide kind of getting at some of the questions you asked earlier about convolutions. It's related to convolutions, these two-dimensional convolutions, but we already talked about that. So what we basically set up here is like the notion of convolution, followed by an activation, usually ReLU, and then there are other, and we've actually talked a little bit, I guess, about fully connected layers in these networks. These are usually at the end of your network, but there are other types of layers that we typically use in convolution networks, and one of them is the pooling layers. And we're going to skip that. We're going to come back to it if we have time. Okay. Oh, actually, we're going to do this first. Sorry. So this is just like another look at what's happening in these convolutions. So this whole notion of sliding, right? So if this is just in a very simple case, if I have a 7x7 input, some certain number of channels, and I have a 3x3, again, the same number of channels filter, then what I'm doing when I do convolution is just to for each time I slide this filter, I get another number. So like I get one number out of being in this position, another number there, another number there, another number there, and there. So I actually get 5. Every time I kind of work my way down a row, I get 5 outputs, and I can go down 5 rows, and so we get 5 by 5 output. I can adjust that in different ways. One way I can do that is through strides. So instead of moving like 1 pixel at a time as I do these convolutions, I can move multiple pixels at a time. So instead of just sliding 1 pixel, like in this case, I might slide 2. What we call that is these convolutions with stride 2. So it moves all the way over to like being in the middle here, and then I do it again, all the way to the right, and this time I'm going to get 3 by 3 output. Right, because instead of kind of centering like in this column, or sorry, in this column and in this column, I eliminate those. So now I have 3 by 3 output. I still have covered all of the pixels in my input. Like there was still, there was still some, like for every pixel there were going to be some of the activations coming out of this are going to, let's see, yeah, each one of these will be a part of some activation, some output, but we've just done it smaller. So this is like a way of kind of getting like rapidly smaller output, and you can continue to kind of play with it. So what happens if we try to do this with stride 3? Well, with stride 1, we just kind of like think of like the center here, we kind of move it 1 to the right, 1 to the right, 1 to the right. Stride 2, move it to 2 to the right, 2 to the right. If I try to do stride 3, I'll take this, I'll go 1, 2, 3, and I'll end up here. But if I go 1, 2, 3 again over here, I'd be off my grid, right? Like that wouldn't make any sense. Yeah, it doesn't fit. But we can make this fit if for some reason we wanted to do stride 3. And we'll talk about that in a second. But there's some like basic math for like to think about what the output size will be here. Dimension of your input. This is always assuming like everything's square, which is not always square, but these simple examples are square. So the size of your input, the size of your filter. So you subtract the size of the filter from the size of your input. That kind of gives you like the inner dimensions. Divide that by the stride. You need to add 1 to keep track of things, and you'll see that when we did stride 1, we got a nice round number. Stride 2, when we did stride 3 here, we did not get a round number, so that doesn't work. Okay, so to be able to deal with this, if we wanted to, there's a notion of padding your image, basically like making it larger spatially and also depth-wise by just kind of like packing around it all a bunch of zeros, so that when you do, so you can put the filter like in this case, we had the 7 by 7 image, but when we add like a layer of zeros all around it, then we can actually center that filter right on the corner, which we haven't been doing before, right? We center it right on the corner, and what happens when we do the filter like dot product is that because the input's all zeros, all those products are 0, and then so they won't contribute anything to that sum. So we're not actually getting anything. We're not getting any signal, kind of like spurious signal that we just sort of created because we had it. But this is getting us some kind of like computationally easy way of allowing us to apply our filter kind of all over the image. And like in this case, what does the output size become? If we pad with zeros by 1, just around the whole image, what's the output size? 2. So I heard a bunch of things, but I did hear same. So yeah, 7 by 7, right? Because if I'm doing stride 1, I start in this corner, that corner, basically like every single entry I'm able to put down a valid 3 by 3 filter. So I get 7 by 7 output. And I can stride with size 3 because I can now go here, and then 3 to here, and then 3 to here. So you know, if you wanted to do that. And notice again, like we've covered all of our input pixels in this way. If you were to build the padding some more and you did like a stride 4, you'd start to miss pixels, and you may not want to do that. Usually you don't want to do that, but there are some ideas, like really convolutions that do that. But anyways, this is the typical way to deal with wanting to be able to produce, say, like the same size output. Okay.
I think there might be some information if you do some padding here, because you know sometimes the filter just sense the gradient. And if you ask some zero field, the gradient.
That's right, like the weights, that's right. So you're exactly right. So when you apply this filter along the edges, those weights that are being multiplied with the padding, they're zeroed out. So like they're not contributing to the gradient.
No, I think it's sometimes the filter just calculates the gradient. Maybe 1, minus 1, negative 1. So they two just minus each other. It just calculates the difference between two pixels. So here
like for certain choices of the weights themselves, you get like a difference. Like if it was like a 1 and a minus 1, you'd see the difference between those two.
Sometimes you learn something about the edges because there is certainly some edges here.
Yeah, like if you were to visualize that, there would be like a what is that, a white edge?
Yeah.
But that's right. But those weights are not contributing anything to the signal to the gradient, so they're not being updated as a result of that of that signal. Does that make sense? Like that's like in the computation, that's actually not contributing. It's not going to learn that edge there.
Is there a way to support convolutions when taking that step right there? Because 1, 2, 3, 4, 5, 5 of the values are not contributing anything.
Yeah. So
threshold, is there a way to adjust it so that it's scaled to only those 4 values?
Because you're multiplying the weights. So for this particular activation, because you're multiplying these weights by 0, they will not contribute to the activation, so they won't contribute to the gradient for that particular activation. But of course, as you move that around, they're going to contribute to a whole bunch of the other activations. So they'll be updated that way.
What I'm saying is the activation function. You have to achieve your threshold with only 4 activations.
Oh, like you're saying, like if you apply a ReLU.
Yeah.
That's right. That's right.
Is there any practice that deals with that? Giving it support?
Yeah, you're saying that I see what you're saying. No, there's not really a thought of how to deal with that.
I guess edges just don't matter that much in practice.
Yeah, it's an interesting question. It's certainly just done for convenience to be able to be able to apply this over like the entire image rather than and to get for instance, get the same size spatial output. Yeah, it's a good question. But you're right. Like it has this has in a ReLU, this is forcing like the weights here. If they're going to contribute to the gradient, they're going to have to be like large. Like these 4 are going to have to be kind of large in general, like on average, to get this signal over into the positive range. Like depends on what the bias is, and to be able to kind of compute that gradient. It's a good question. I mean, I don't think I've ever seen anybody kind of think about how to deal with that, or felt like it was necessary to deal with that. But again, because you're taking the same filter and you're creating this whole activation map using this filter, like the weights are being shared in each of those activations. So it's you're seeing it over and over and over again. So it's the aggregate of how these weights are being applied across all of this that is contributing to the gradient. So all weights end up contributing. But you're right. In this particular case, there is kind of this thing of needing to be larger than the come. It's a good question. That might be something to explore in a final project. Is there some way to? Yeah, is that important to deal with? Is there some strange behavior that happens with that? I don't know the answer to that.
For the next layer of this convolution in padding, the outer layer is just computer from the zero padding. Zero padding is involved. And for
Like
the,
in the next layer, we might use zero padding again. What you're saying?
yeah, and
We can choose to do zero padding in all the layers if we want to. We don't have to.
so after some certain amount of layer, all the output is computed on the padding. Because after 2 layers, 2 rows are computed on the padding. After that, 3 rows.
No, I don't. I'm not sure. I follow you. You would just like in the next, like if this was not, if this input here were not from the first layer, it was like however many layers deep, you still just have zero. You have zero padding, and that would just produce you another spatially extended filter map. It's not going to incorporate more zeros. If what you're saying is like the receptive field is like somehow has more zeros, but it's still not that way because it's not adding zeros. It's just like there's just those, in each of those layers there would just be like a boundary or a border of zeros.
And that without zero padding, in each layer the dimensions are reduced.
Right.
But for this trick,
Yeah, you keep them the same.
the same. But the real size, which is without padding, is just in the center, and by adding to the depth, the real
They're getting bigger and bigger.
smaller and smaller, and I mean this might be a reason to not add to the depth.
Oh, I see. Like, yeah. So there are other ways. So we typically want to do this kind of padding, and then reduce the size of our the spatial extent of our output by either doing striving or applying pooling. And I think we're going to get to pooling here really soon. So yeah. Let's see. Right. So we have a bunch of layers of these things. Yeah, we're kind of running out of time, so I'm gonna. So okay, let's just answer this real quick. So if I have 32 by 32 by 3, and I apply a 5 by 5 filter with stride 1 and pad 2, I do 10 of those filters. What's my output volume? Yep. So it's 5 by 5. So the padding of 2 allows me to put the 5 by 5 right at the center, put it right at the corner, and still be able to do a valid convolution or valid kind of filter dot product. And I have 10 of these filters, so I'm going to get 10 channels. So I do get 32 by 32 by 10, and you can verify that with a fancy formula that we put up earlier. How many parameters are in this layer? This is important. How many parameters are in this layer? So like parameters are the weights of the filters. Okay, so each filter is going to give us 25, and then there's going to be a bias for each of those. That's going to give us 26, and then I have 10 of those. Oh, whoops, we forgot the depth. Right, so this is being 25, we're going to multiply by how the number of channels, so there's 3. So 5 times 5 times 3, 75, plus 1, that gives us 76, and then times 10, 706, or 760. Let's see. Yeah, so the point of doing that is remember that like it's the filters that have the weights, right? It's not like that, as we like do this convolution and get the output. Those aren't the weights, that's the output. So what's nice about this is like if we were this fully connected, this would be huge, right? This would be 3072. There'd be 3072. Well, the output's kind of a different size here, but you already have like way more weights. An order of magnitude roughly more weights than you have in doing this, and yet you're getting something of comparable, usually actually greater capacity. Okay, so I won't do this right now. You can take a look at those in the notes. Oh yeah, this is something really important to note. we've been thinking about like 3x3 convolution, 5x5 convolution, like the size of the filters. You can do 1x1 convolutions, right? Which means that like your filter is just like the size of a pixel, and then because you always have the depth of your filter is always the same size as the input depth, you can basically just preserve the spatial extent and then just change the number of channels. And 1x1s are used all the time. There's different kind of theoretical reasons to do that, but you have these. All right, let's kind of get to. You don't want to do that? These are big. Okay, cool. Pooling. So, pooling is a really simple operation. There's different kinds of pooling, but the idea is simply to like downsample the image, preserving the number of channels, but shrinking in a significant way the spatial extent. And the idea of pooling, like the reason it's called pooling, is that you usually think of this as you choose some sort of filter size for your pooling, and then you do your downsampling, your reduction, by somehow taking, like in this example, you take 2x2 filters. Here we just write 2, so we're just kind of there's going to be no overlap. And in each of these pools, in each of these kind of 2x2 spatially extended pools, we're going to take the maximum value, in this case of max pool, we take the maximum value of that, and that will end up in this now downsampled to smaller output. It's super simple. There's nothing more than just like a very simple way of going from, like in this case, this will be having the spatial dimensions. Max pooling is often used. The idea here is like, as you pass these filters along here, you're trying to capture, like, you can think of this as like, if you have a large number here, like you've captured something kind of big happening in this image, given like whatever the filter is doing. And you want to preserve that in the pooling, so that like that's something big happening kind of in that region. And it makes you, it's a little bit like a regularization, because it makes you like a little less sensitive to exactly where these edges or corners or whatever big thing is happening in that pool. It makes you less sensitive to where exactly it is in the 2x2 in this case pool. There's also like a notion of average pooling. Instead of just taking an average, you just average over the whole thing. And then typically, what you want to do at the end of your network is to take your activation maps. Let's see. Take your spatially extended activation maps. I have a slide there. You at that point, you can use them in a number of different ways, but you want to take them and you want to stretch them out into a vector. You do however many fully connected layers. Maybe you don't do any. You go to a softmax layer, so you can apply. If you're doing classification, you can apply your cross entropy loss, and then do your classification. And this would be kind of like like what your whole convolutional architecture would look like from start to finish. Yeah. Is this the last one? Yes. Okay. Sorry, for some reason I thought there was a better slide there. You think about, go all back to the beginning. I'm going to go back to this slide here of Imagenet. Imagenet is set up in exactly this way. So there's convolutions, certain number of filters produced to give you the next set of activation maps or feature maps. And then eventually what's done is that you take all of this output, you stretch it out into one long vector, and you do a couple of fully connected layers, like what we learned about last time, just these neural networks with just hidden layers. And then if you're doing classification, you'll want to do something like a softmax to a cross entropy loss. If you're doing something like regression, then you might just have like a linear activation and go to like a mean root mean squared error, loss, something like that to get to do regression. But that's that's the basics at the end. You need to go to this because you need to get to a position where you can apply something like softmax. This class we mostly think about classification. That's why I say this. You got to get the all of the outputs into a format where you can apply the layers necessary to feed into your loss function. Okay, so summary. Question? Yeah, go ahead.
How do you do a dropout?
Yeah, it's funny. I thought we were going to drop today, but actually we do it in the context of the code.
Oh, okay, next time.
Okay, so summary of what we've gone through with convolutional networks. So, yeah, the way that the way like filters and activations, you might have some pooling layers in there, and you will follow up at the end with some fully connected layers so you can feed into your loss functions. Yeah, so I kind of mentioned this, and we're going to see this as we go through through our history lesson. The trend is definitely going to smaller spatial filters, but much more depth. And the reason for smaller spatial features is as you go deeper, you're just adding so many more parameters, right? So the parameters are determined. If you have a 25 by or if you have a 5 by 5 filter, that gives you 25 parameters per channel. Depending on how many channels you have, you can multiply by that. But you go to 3 by 3, that's 9 times the number of channels. There's a third essentially of the parameters as a result. So because we're trending towards convolutional networks, the trend's been towards deeper architectures. We need to somehow control number of filters. So one of the ways to do that, or the number of parameters. So one of the ways of doing that is to just make them spatially smaller, and then just control the number of channels at each layer. Yeah, so this is interesting. There's definitely pooling and fully connected layers are definitely a big part of earlier networks. Again, we'll see this in our history lesson, but there's definitely a trend to going to straight just convolutional networks, and the way that you'd work in feeding into softmax is you just go you can do, well, we'll see some of it. There are certain pooling operations like global average pooling, which reduce the full, whatever spatial extent you have in your last convolutional layer. You just average everything there down to one, so a 1 by 1, so that the number of channels you have is the size of the vector, and that feeds immediately into a softmax and into your cross entropy loss. And here's a kind of a regex for what these look like. But as you'll see, these trends are definitely true. So okay, so we start kind of convolution through time, starting in 2012. So not that far ago. Next time. Is just to be able to, it's basically it was to apply neural networks to images, do it in a way that preserve, have a lot fewer parameters, but preserve spatial
statistics.
On the first place,
Right, so like in convolution,
we didn't answer it, so.
because you're doing weight sharing, you're really reducing your parameters. But you're also, like, those things are not learning, but the like statistical properties of whatever the size is. And whatever.
That's kind of like you said, creating the beginning.
Right.
And still comparing areas.
Yeah, exactly. And by doing that, you're allowing the filter to kind of like learn like an abstract kind of property of, like an abstract kind of like statistical property. Yeah. Yeah, perfect. Thank you.
I don't know, I find it easier for me to understand it because I draw it, so it's just like I draw and make it like this is the actual information.
So it is taking each of this and multiplying this.
Sure, yeah, that's a single number that you have as 3 5 ways. Or you can think of it like you reduce all these maps, which is why later into it's the same. The weights are the filter. The filter has, so like what we're saying when we do this. Yeah, it's
Yes, this is a function I had used for.
so it's best way to look at this is like kind of cut into like voxels or something, and
No, like there's a.
so and actually this should be like I have a whole bunch of these.
Yeah, this. Yeah, something like this. This is what I use.
Oh, I think mine's different than that.
So
For homework lunch?
Yeah.
each one of these cubes there's going to be a number. It's the width. Right? So like this is
Sorry, it was like
1 1 1.
How did you like? Because I looked it up and it had my answer. I can't like exactly the same.
And so forth. Right?
So
So
I need to find a way to different
that's
And you're training or this book
the problem is 500 makers, right? It's 501. This is like 5,000 or something.
it's the weight of the filter, the weight of the filter
This first
plus
one,
their bodies.
and then put that as a per filter.
That are being
And then for the next one, we have it.
Yeah, so like this produces this will produce some other size thing. And you're essentially just like yeah. So like so
It looks like
each filter has just
and
one.
there's like one. It was like
It's just one
an
channel.
axis. So I think it was it was np dot axis.
And
And then add row each time. So you
whatever it
that
is.
way.
And to this whole thing is adding one.
So you just go that.
And one more.
Yeah. Yeah, I would just,
Right, plus.
what was it? It was a dot product. Dot product related. I kind of stuff like that.
Totally like focusing on that. Why we
Yeah, and then
what's the
We'll make them 0 so that like when we do the
yeah,
when we do the entry wise like dot product,
so yeah, I did some.
this is multiplying the weight of the filter by a 0. So that's becoming a 0. So it doesn't contribute to the output, to the application, to the feature.
What that is, I think it's weird.
I mean, you could pattern with anything, but it makes sense to do a 0, so it's not.
okay, so are we all the edges 0 like
Yeah.
walls? Okay.
Yeah, but yeah, when you